Hi and welcome back to the channel. Today I'd like to talk about gain product bandwidth of an op amp. Right, let's talk about op amps. Without those resistors, if you put a wire between there and there, you'd have a gain of 1. Take the gain of wire away, you have open loop gain, which in the case of say an op amp like a 741 is 105-ish dBs, but its frequency response at that gain is quite small. And it drops off once it goes past that point, which is sort of the break frequency. Now, if we look at the sort of a rough diagram of the gain versus frequency, you can see just shy of 100 Hertz, the gain starts straight away to fall. So, by the time you got down to 10 kilohertz, you're down to like 50 dBs, but it's still a lot of gain. So what do we normally do? We normally put a feedback resistor and an input resistor and control the gain via the feedback. So here we have 100k on the feedback, 10k on the input. 100 divided by 10 is 10. So we get a gain of 10. Now, if you do the sums and convert a gain of 10 into dBs, it comes out as 20. Because the formula for converting to dBs is 20 log 10, the V out divided by V in. So V out divided by V in will give you 10. The log of 10 is 1, times it by 20, you get 20. And that's how it works. And so what happens then, as you can see, we've now got a gain of 20 dBs, and it's flat, or flattish, right up to about 180 kilohertz, where it hits the slope there, and then it follows it down to about a meg. So, you want to look at signals up to, say, if you're just doing audio, 3 kilohertz. If you're just doing speech on like YouTube and you want an amplifier, 3 kilohertz is enough. Much above that, it's kind of wasted. But, anything around your circuit, small cap, caused by the circuitry wiring between the output and the input, and that's not too much, because at these frequencies, caps can be the value of the capacitor can be quite small, and so the amplifier can become unstable and go into oscillation. And quite often you won't know it. Current consumption will go up because it's working harder. It might get hot because it's thumping from rail to rail, and the output might be sound a bit distorted. But without looking at it at a scope, you may not always tell that it's hooting away at higher frequencies if it's not disturbing your low level audio too much. So what do? Well, we go back to our circuit. Hey, and look, we add a capacitor in parallel with a feedback resistor. Now, quite simple to do. Just stick it in parallel with that resistor. And what we're aiming to do is we're aiming to look at whereabouts do we want our highest frequency. So like, if we're doing audio to 3 kilohertz, let's say we don't care about much above 10 kilohertz, give us a bit more headroom. So what we want is we want a capacitor whose impedance at 10 kilohertz is roughly the same as the feedback resistor. So then, of course, by Ohm's law, you'll have 100k. If the impedance of the capacitor is 100k, that divides it down to 50k. So now you've got 50k feedback, 10k on the input. You've now only got a gain of 5. So your gain is halved. And because it's effectively an RC filter, the gain will reduce at 6 dBs per octave, which means for every doubling in frequency, the output will drop by 6 dBs. Or the same slope is also 20 dBs per decade. It's just two different ways of looking at the same slope. And so what that will do is it will allow you to start the slope early. And so, frequencies up here, over 100 kilohertz, which would have been a problem before, and now not so much of a problem because the gain is falling away. And so you'd need a much bigger signal to get you into oscillation. So quite simple, just a matter of adding a capacitor. Now you'll know, well, we may all know, that the impedance of a capacitor is easily calculated. It's 1 divided by 2 pi fc, so 2 times pi times the frequency times the capacitance, all divided by 1. And so if we're looking at this and we want to go, say, at 10k, the bit we don't know is the capacitance value, but we know what the impedance wants to be. So we can just rearrange the formula easily so that then the capacitor is equal to 1 over 2 pi, the frequency, and the impedance we want, 100k. So you plug that into your calculator and you'll come back with a capacitor value that you strap across that, and lo and behold, you've now tailored your amplifier to the correct frequency. So we would be looking at, for a 10k roll off, we want a capacitor of about 160 picofarads across there, and that will be job done. We will have gain of 20 with a nice defined 6 dBs per octave slope, and we are now controlling with our feedback the gain and the high frequency response. Yeah, we could stick if you wanted to, we could stick another capacitor, do the same sort of calculations, and we could put a slope at the front to tailor it, because maybe we don't want to go right down to sort of very low hertz. If you don't need to send information at those frequencies, filter them out. If you filter out above 50 hertz, you shouldn't. It will reduce mains pickup. But that's about all I was going to say. Just a quick, simple talk on changing the feedback and tailoring the frequency response of an op-amp used for audio. I hope that was of help to people. If I've made any mistakes, down below, comment. If you like it, click the like button. If you haven't already subscribed, hit the subscribe button, and share it, make comments. It all helps. I'll catch you on the next video. Bye for now.